career. So he got his PhD in 2006 in statistical physics at USP. And as many Brazilians during the final year of the PhD, he did his BEPI, right, in Grenada. Then he had a postdoctoral appointment, again in USP from 2006 and to 2008. And then he entered as an assistant professor in the Federal University of Paraná, where he stayed until 2014. And from 2014, he's now a professor at USP. And he's an expert in statistical physics and in non-equilibrium thermodynamics.
I don't know if I'm an expert.
Let's say that you are, at least locally. And today's talk is about that, and is about non-equilibrium thermodynamics of collective heat engines.
Thank
the floor
you.
is yours.
That's a joke, but that's true. I don't know if I am an expertise. I think no. But I'd like to confess that I am very happy in this research I have investigated since 5 years ago. Are you talking about the non-equilibrium thermodynamics? Only in the end, are you talking about in collective system? Probably in the most of part of this colloquium, I will review or provide an overview about the main aspects about thermodynamics, non-equilibrium thermodynamics, okay? As a motivation, probably one part of this colloquium, are you talking about a heat engines? We have learned the concept, the idea of heat engine since in the thermodynamics course. And basically, you receive an amount of heat from the hot reservoir from now on. 2 means the hot reservoir, 1 means the cold reservoir. So the system receives an amount of heat from the hot reservoir. This system means, for example, a motor or another kind of engine. It partially converts into work. The second law of thermodynamics forbids this, the integral conversion. So one part of this energy receives is rejected to the cold reservoir. Okay, this is the sketch of a typical heat engine. Okay, in the thermodynamic equilibrium, typically we are dealing with macroscopic systems, large systems in the equilibrium state. The fluctuations is not taken into account. The time independence of quantities are not typically not taken account too. For example, we have this, a sequence of process. These processes are typically generated by changing the volume or the pressure, for example. It can be the temperature. Okay, and an important point. From this state, for example, this state, any change of states are generated via quasi-static process. It means we change very slightly changes in the system. Each is sufficiently small changes. We wait the system relax to the equilibrium and so on. This means quasi-static process. So a sequence of infinitely many is very, very, very small changes, and we wait the system to relax. Okay. Okay, and another important part is the efficiency of a system, which is the ratio between the work, the total work, over the heat received from the hot reservoir is always bounded by the Carnot efficiency. Carnot efficiency is very important because it's equivalent to the second law. It's a consequence of the second law of thermodynamics. It solely depends on the temperature of the hot and the cold baths. It does not depend on the details of the system. In this slide, I provide you a very short review of the thermodynamics, the equilibrium thermodynamics, okay? Okay. As I am going to show you in the next slides, you can also extend these ideas about thermodynamics, these ideas about energy conversion, this energy about Carnot efficiency for a nanoscopic system. But there are some differences, as I am going to show further. Before this, I would like to introduce you some concepts, some ideas about irreversibility. Along this talk, I will talking about dissipation, equilibrium, non-equilibrium, and all these concepts will appear, okay? A part of this, we take, again, in the equilibrium case, we have an entropy function. This is a function of extensive quantities, and if you take the ds, I forgot the expression, the ds, the infinitesimal change of entropy, you can write in this way, okay? This is the derivative of entropy with respect, for example, to the energy, and this derivative is proportional to the inverse of temperature, or in the case of the derivative is taken account with respect to the volume, this is the ratio between the pressure and temperature, and so on, okay? This is the formulation of an entropy function as a function of extensive properties, and this function should be consistent with the second law of thermodynamics. Why I am going to show you? Because some concepts about irreversibility, entropy production, also appears in this macroscopic formulation from a standard thermodynamics course. If you take one isolated system, divided in two subsystems, 1 and 2, or A and B, if you take the time derivative of this expression for this composite system, you will have this. The entropy is additive, so this quantity, the total ds is dSA plus ds2. But we have, since the total system is isolated, the energy 1 plus energy 2 is kept constant, or UA is plus UB is constant. The same holds for the volume and the same for the volume. So after taking account this constraint, you have this form. Until here, okay? Until here, okay? Okay. Why this expression is interesting? Because it refers that this change of entropy can be written as a sum of this quantity. This quantity is referred as a thermodynamic forces. For example, if X is the energy, this is proportional to the difference of temperature. If X is the volume, this is the difference of pressure. If this X is the total particle number, is the difference of chemical potential. And you can interpret this variation of entropy is due to the thermodynamic force time this quantity. This quantity is a flux, So this quantity is always positive. This quantity is always positive according to the second law of thermodynamics. Since it is always positive, this quantity is positive too. Of course, both can be positive or both can be negative. This only means a heat flux from one hot to cold subsystem, or a large pressure to a lower pressure, a large chemical potential to a lower chemical potential. So this quantity is also referred as entropy production, and it is not a property of the system A or B, it's a property of the composite system. This is when this is positive, we have this. This is different from 0. and it vanishes in the equilibrium regime when the temperatures are equal, when the pressures are equal, in the case you have variation of pressure, and so on. Okay, another interpretation of this quantity, let's consider the subsystem B is much larger than system A. In this case, the subsystem B acts as a heat reservoir, as a thermal bath, And the change of entropy in the system is solely due to the subsystem A. And you can write the above equation in this way. This quantity is this one. It is always positive or at least zero. And is the entropy production. This is the heat flux, because from the point of view of thermal bath, the changes, the heat exchanges will not affect the thermal bath properties. So from its point of view, it's reversible and it operates as a heat reservoir. And this is proportional to the relation between heat and the temperature. It's analogous to the Clausius relation. So this equation, it's important because it tells us the time variation of entropy of a system is the difference between two terms. This term is always positive and corresponds to the entropy production. And this term is an entropy flux, is the entropy flux in which the system A exchange with the reservoir. This is the entropy production due to the irreversible process. In the steady state, you have this equal to this, and you have only two possibilities. Both are zero in the equilibrium, and both are positive in the non-equilibrium. So, above macroscopic description I've just introduced you, provides a first idea about reversible and irreversible process. A reversible process do not produce entropy in the non-equilibrium steady state, in the steady state. On the other hand, a non-equilibrium process, irreversible process, are those produce a positive entropy production in the steady state. Now, the next slides, I will derive this equation, but from a stochastic description, okay? Okay. Now, I have shown in the first slide a typical heat engine. In the thermodynamics course, the system is a motor, for example, is a macroscopic engine. But these ideas about energy conversion, about useful work, about the system can be projected to be operated as a refrigerator. These important concepts in thermodynamics can now also appear in this nano system. This system is a quantum dot, for example, placed in contact with two thermal baths. These ideas about energy conversion also appears here. This is what I am going to show you along this talk. But there are three remarkable changes. First, here the role of fluctuations can be important. Here it's not taken account. Second, typically these systems operate out of equilibrium. This, we typically consider them...
When you talk about fluctuations, you mean statistical fluctuations. So you are always in a stochastic setup when you talk about fluctuations.
I consider of course, you also have fluctuations here, but these fluctuations are not typically taken in account. But here, they can also be included.
Yeah, but my question was more trivial. What is the source of the fluctuations? A stochastic term in the, let's say, if you look at the equations or whatever, what is the...
Good question. Just let me see if I know how to answer you. Of course, you have a nice stochastic source, and but it can be comparable with the other quantities.
Okay, so in that case, it in stochastic setups, the fluctuations arise because you have a stochastic term in the
Yes,
equation.
yes,
Okay.
yes. Okay, here, this system typically operates out of equilibrium. Third difference, here, the useful work comes from moving pistons. Here, it comes from probability currents, as I am going to show, okay? In order to show these features, in order to show these main features, first you provide a brief overview about stochastic process, okay? Okay, we are dealing typically with Markovian stochastic process, evolving at a continuous time. Here is the probability distribution. P is the probability of the system is a given state M. This probability system is really governed by this master equation. The master equation takes into account the time evolution of the probability of the state N of a system. Note, we have here again term. All configurations M that gives rise N. This term contributes to the increasing of this site. And this is a negative term. This term takes account the configurations which will emerge from M, okay? So, and this is the summation over all different configurations. This term in the parentheses is also referred a microscopic current, current probability. Okay. For a stochastic process, Markovian process evolving in continuous time, this is the framework used to find the probability distribution, okay? This system will evolve to a steady state in which the left side vanishes, and we have two possibilities in the steady state. Each individual term be zero. This is the equilibrium steady state. In this case, this condition, also named the detailed balance, means the probability distribution in Boltzmann-Gibbs-like. So this is the typical, when the detailed balance is obeyed, is fulfilled, we have this, and this is the typical scenario of the graduate or undergraduate statistical mechanics course. One system placed in contact with a thermal bath, one system placed in contact with a thermal or particle bath. Okay, this is the scenario. In this case, typically the transition rates cannot be taken into account because you already knows the probability distribution. This is the system Hamiltonian. On the other hand, when this is not zero, but the summation is zero, we say the system will evolve to a non-equilibrium steady state regime. What means? It means we have internal currents in your system, but their summation are zero. It means the non-equilibrium steady state regime, okay? It means, typically in this case, the probability distribution. No, you are sum, all configurations M different from N. No, we are sum over M. Yes. Okay. Given an N, for example, when you sum for all different, they are zero, okay? This is typically the non-equilibrium steady state regime, okay? To make an analogy, what is equilibrium, what is non-equilibrium, and what is non-equilibrium steady state regime? I don't know if the analogy is good. I saw once in a seminar and I liked it very much. The equilibrium is this. Nothing happens. The changes are so incremental. For example, we have your system at the same temperature of, we have a system placed in contact with a thermal bath. They are in equilibrium. Sometimes your system exchange a small amount of heat with the bath, and after the bath gives an incremental change, and so on. Your system, for example, the internal energy, in this case, it fluctuates. We have small fluctuations of mean energy, for example, and this obeys the typically relations of the canonical ensemble, for example. This is the equilibrium case. The non-equilibrium is this, all changes, okay? And this, it's alive. You have internal, we have internal currents, probability currents, but all their summation are zero. This is what it means, okay? I don't know if the analogy is good, but it's something like that, okay?
I repeat the question.
That's an important question. This is an important question. Both the probability the probability in equilibrium and non-equilibrium typically does not change of the time. But in the equilibrium case, they are Boltzmann-Gibbs-like. It means the process, the system are placed in contact with a thermal bath, one thermal bath. These fluctuations are ensemble fluctuations. In the non-equilibrium steady state, we have internal currents that favor some transition. For example, we have here a three-state system. We have this transition, P, QP, for example. If Q equal P equal 1/2, this system will evolve to the equilibrium case. But if Q is different from P, in the steady state, one current will be favored with respect to the other. Note that we have a flux in the clockwise and another flux in the counterclockwise. In the equilibrium, both are equal. In the non-equilibrium, one is more favored than another one. I don't know if this is an analogy that distinguishes equilibrium from non-equilibrium. Okay? We speak something, William? Okay? But mathematically speaking, equilibrium is this, is equivalent to this, we can show. Non-equilibrium is this. Note that in this case, it means we have a flux favored along a direction. Okay? Okay. Now, okay, along the next slides, okay. In the first slide, I described some ideas about first law, second law of thermodynamics, reversibility, irreversibility from a macroscopic point of view. Now, my idea is to talking about these concepts, but from a stochastic point of view. The stochastic approach I will take in account is this, the Markovian process described by a master equation, okay? The next question is how to derive the first and the second law of thermodynamics for this class of system, okay? This constitutes the scopus of stochastic thermodynamics. I don't know if I have a precise definition of stochastic thermodynamics, but in my opinion, it's an extension of thermodynamic law for systems operate at the nanoscale, taking into account the framework of stochastic process, okay? Basically, if you are describing a thermodynamics, you have to be able to define, to introduce a second law and a first law of thermodynamics. How these laws appear in this stochastic process, okay? There are different formulations of the second law. For example, these both are similar to the macroscopic case. The efficiency is always bounded by the Carnot. We have a limited performance of heat engines. This is not entirely different, but somewhat different, a positive entropy production. Entropy production, sorry, forgive me. The entropy production I introduced you previously in that example, I told you that the entropy production is always positive. Here, the average entropy production is always positive. A different definition, a different formulation of a second law that does not appear in the macroscopic context, but appears in the stochastic is the fluctuation theorems. For example, this one. Note that, according to this, you can also obtain along a trajectory, along a measurement, a negative entropy production. But on the average, they are exponentially suppressed by its positive value. This is the fluctuation theorem by Crookes and Jarzynski. Note that it does not correspond to a violation of second law, because on the average, we can show this is always positive. But the stochastic approach allows the obtaining negative entropy productions, but they are exponentially less likely than positive one, okay? Another interpretation is this. You know from the thermodynamics, macroscopic thermodynamics, in a reversible, when your system is placed in contact with a thermal reservoir, the work performed by the system is proportional to the difference of Helmholtz free energy. Here, when you have an irreversible process, they are different. This is what means this fluctuation theorem, okay? This is another formulation of second law. And in the line you asked me, we have another interpretation that are the TURs. I'm going to show you now, only this version, but now it relates dissipation, entropy production, and the fluctuation of a quantity. And this, for steady state forces, this rate is always larger than 1, which means another interpretation is this. If you want to increase the precision, you should increase the dissipation, or the vice versa. If you decrease the dissipation, it's necessary to increase the precision. Okay, these are new formulations of the second law. It does not appear in the macroscopic context, but it appears in the stochastic approach. Okay.
So is this an ansatz, or is this some proof?
No, this can be proved for Markovian process. This can be proved for.
How long do you have to wait? So.
If you take into account a Markovian process in which transitions obey, I'm going to introduce in the next slides the local detailed balance, you can prove this, both.
don't you have to wait a certain amount of time? I mean, if you want to average
in
over-
the steady state, if you take a stochastic trajectory from one state, from an initial state to a final state, you can prove this, both. Okay?
I mean, I think the question was related to my first. So here, all the averages and so on are taken with respect to realization of the stochastic variable, right?
Sorry?
I mean, you are averaging over realizations of the, stochastic process. You agree, right?
Yes.
Okay.
Yes, yes. Okay. Of course, in this case, you can evaluate both over all stochastic trajectories. Okay. 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 Now, I introduced the idea of stochastic thermodynamics. I introduced different formulations of the second law of thermodynamics. Now, I will derive for you this relation for the stochastic context, okay? For Markovian process, okay. If you take in account the same master equation as before, I only rewritten in this more convenient way, okay? That here is the transition rate from N to M, and here is the transition rate from M to N. Is the same master equation as before, okay? Now, if the formulation of first law and the second law of thermodynamics requires two definitions. First is the definition of entropy. We assume that the entropy is the Shannon entropy. We are assuming this definition of entropy, okay? We are assuming that this entropy definition considered in the equilibrium case is valid in the non-equilibrium case. By taking the derivative, the time derivative of this equation, by inserting the master equation, we can rewrite this equation as a sum of two terms. Note that this is always positive, because if this is positive, it means the logarithm of the ratio is larger than 1. If this term is negative, it means the logarithm is smaller than 1. So this is always positive and can be recognized as the entropy production rate. This second term is related to the heat entropy flux, okay? A second definition is to define this as entropy production, okay? So it's a second definition. In other words, the construction of a stochastic approach for the second law requires two definitions. The first is the entropy definition. The other is the definition of entropy production, okay? So in the steady state, this term vanishes and you have the equality between both terms. In analogy with this one, sorry, I'm going back several times. In analogy to this way, okay? Okay, now I derived a formulation for second law. Now I am going to derive the first law of thermodynamics. We start the definition of energy, mean energy, as an ensemble average, okay? If you take its time derivative, you have this. The first term I define it as work. This work is typically associated not necessarily to moving pistons, but time variation of energy with respect to a given protocol lambda. For example, if I take the time derivative of the time derivative of energy with respect to the magnetic field and so on. This term is the chemical work. It's actually a heat, a chemical heat, and it relates to the variation of a particle number. And this is the definition of heat, okay? So, in other words, the formulation of a first law of thermodynamics in the stochastic context requires the definition of a second law I showed you previously, and the first law I'm going to show now. This is the work. This is the heat, okay? Work is associated to changes of the energy levels with respect to a given protocol. Heat is typically associated with time variation of the probability, okay? This is the heat in the stochastic context, okay? But we know that this definition, okay, are definitions, but how is the connection between this and the model thermodynamics? When I say the connection with the thermodynamics, I mean the connection with temperature, for example. In the equilibrium context, I have one entropy function and a function of these extensive variables, and the connection with thermodynamics is performed by taking its derivative, by taking this derivative. Here is the connection with the thermodynamics, because typically, in the equilibrium case, we have we use the Boltzmann definition. It's a definition of the number of the density of states. But if you want to connect with the temperature, it's necessary to take this derivative. And in this case, we need a similar assumption. We need to relate the probabilities with the temperature. And we typically consider these ansatz. We assume that the ratio between transition rates are proportional to this. For example, and if you have a chemical potential, we assume this. This is the framework typically considered in the stochastic context for relating the probability, the transition rates, with macroscopic variables. This is what I'm going to show here. Okay? When we take in account this assumption, it's possible to relate the entropy flux with the ratio between the heat rate over the temperature.
So this is independent on M and N, right? So we are saying that any the ratio between any transition.
Depends. No, you are absolutely right. No, you are absolutely right. Sorry. Okay?
A temperature.
Good question. It's a definition of a temperature. When you take this assumption, here is the temperature, the inverse of temperature. It's a definition of a temperature in this context.
But does it have any physical interpretation?
Good question. I don't know if I have a good answer for you, because this, I will use an argument, I don't know if I convince you, but in the non-equilibrium case, for example, if you have different temperatures, different chemical potentials, for example, the system will evolve to the non-equilibrium case. Okay. If you take only one, it will reduce to the equilibrium, and this corresponds to the temperature. So I'd say, in principle, if you consider a setup experimentally in contact with two temperatures and use these definitions, I'd say, in principle, you can compare. But I have not reproduced you. In any way, I'd say this is an ansatz, because you need, if you want to It's a definition, the temperature in this case. I don't know if my answer is satisfactory. Maybe not.
No, no, okay. But that beta will not depend on the states, M and N.
In principle, not. No, in principle, not. If you have an infinite thermal reservoir, not.
Okay.
Okay? Okay. When you consider this, again, this is an ansatz. This is an ansatz. This ansatz provides you to obtain a temperature and the chemical potential definition, okay? Okay. So when you do that, this entropy flux, this relation I deduced previously acquires a Clausius-like form, okay? So this is the connection with the thermodynamics in the present case. Okay, summarizing, everything I have discussed. Equilibrium system, the detailed balance is fulfilled. The system will evolve to the Gibbs distribution, and you have zero entropy production in the equilibrium steady state. Non-equilibrium system, the detailed balance is violated. The probability distribution can be unknown. In some cases, of course, from a theoretical point of view, you can solve the master equation and find. But it not necessarily, probably most of cases, it does not have a Boltzmann-Gibbs-like form. And you have positive entropy production, okay? Okay, now, since I have discussed several contexts, I hope I am not confusing, I hope to be clear. Let's exemplify in a simple system, okay? In a simple system. You have one system. This system can be only empty or occupied by a particle. If it is empty, the energy is 0. If it's occupied, the energy is epsilon 1. Do it to the thermal bath 1. Epsilon 2, do it to the hot bath, okay? Okay. If you're writing down the master equation, we have this. Since P1, the probability of being occupied is 1 minus the probability of being empty, you have only one variable, and this is the steady state solution, okay? If you're writing down the steady entropy production, we have this form. I am going to show this is always positive. Okay. So if it is when it is positive, it means non-equilibrium steady state regime. But in some situations, it will be 0. It will be 0 when we have this 0, it's equivalent to the detailed balance for both thermal reservoirs, okay? Okay. Now, if you perform the connection with the thermodynamics, you can relate this transition rate with the temperature, the associated thermal bath. And here is, in this case, is the difference of energy, okay? In analogy, what I have done previously. And if you insert this into the entropy production, you arrive at this form. Note that it is always positive. This can be positive, this is positive. When this is negative too. So the product is positive, as should be. If you calculate the heat, we have this expression. Note that this acquires a Clausius-like form, okay? Interestingly, if you evaluate the mean heat associated with the cold bath and the mean heat associated with the hot bath, we should obey the energetic balance must be consistent with the first law. So we have the sum of this is the negative of power, or useful work per time. So this system, this power can be negative, and if you calculate this ratio, it is this. Which means, in some situations, this small setup can operate as a heat engine. And in the macroscopic world, it does not make sense this, because we have a macroscopic, a large system, a motor, and this you can talk about work efficiency. But we have the same concepts, but for this is a nanoscopic system, okay? But you also calculate an efficiency. Note that it's always lower than Carnot. But if you choose the energies in this way, this system, this small system, can operate as a Carnot engine. In this case, correspond, when you have this, the entropy production is 0, which means the system is in the equilibrium state. So in the non-equilibrium state, the efficiency is always lower than Carnot. Only in the equilibrium case, the system operates as a Carnot system.
Sorry, I failed to get the difference between epsilon 1 and epsilon 2. So
Yes, yes,
tell me
yes.
again, tell me again. I failed to get the difference between epsilon 1 and epsilon 2. What is the difference between epsilon?
Good question. In this setup, maybe, but let's change, for example, let's change epsilon for a magnetic field. You have a paramagnetic system.
Okay.
And one contact with the code is age 1, is the magnetic field reads age 1. And the contact with the hot bath is age 2. This difference, the energy, the power can be due to the difference of magnetic field.
I see.
I mean, when you have different contact with thermal baths, to each contact with associate a different magnetic field. This is the source of power, okay? Okay, in this case, the efficiency will solely depend on the ratio between magnetic fields. Of course, for this simplest system, okay? So the question is, this system operates out of equilibrium because the temperatures are different and the energies are different too. When the energy and the temperatures are projected in this way, this system operates as an equilibrium system, and the probability distribution Boltzmann gives like. But even in the non-equilibrium conditions, it can operate as a heat engine, okay? Okay, so this is the message, probably the first message of this talk, the first part of this talk. Now I will extend this not for a two-level system, state system, but for a collective system, which will have the similarities and what will we have in different aspects. Okay, you can find more details in these drafts. Okay, and you have the same, we have here a collection of interactive system. It is also placed in contact with two thermal baths as before, and you assume the Ising model like, okay, we have considered in this case a three-state system. We have an Ising model like, we have the same master equation, of course, for square topologies, you have not exactly solvable, but you can consider a mean field-like approach. In the case, all units interact with all units, and in this case, your energy system acquires this, where n plus n minus are the number of units in the up state, down states, and so on. I mean, in this case, all two interactions, the system is fully described by the number of particles in the positive and negative state, from the conservation of the number of particles, and 0 is n, is the total, minus n plus, minus n minus. Okay. If you take the thermodynamic limit, you can also define the transition rates in this way, okay, and you acquire this form where here is the probability of each state. This is the probability of this, okay? Okay, now let's, what is the work source in this case. In this case, in this particular case, I choose the work source coming from biased force. This force favors transition in the counterclockwise direction when the system is placed in contact with the cold bath, and the other way around when it's placed in the hot bath. Okay, this is a particular choice of work source. We can also consider other kinds of work source, such as time variation of energy levels, as I showed you before. In this case, we choose the work source to comes from a biased force. Okay? Okay. So plugging this for the actual case in the transition rates by solving the master equation, okay? It's the same as before, but of course it's a bit more cumbersome because the master equation in this case is not linear. By solving this, believe on me, you can solve this exactly, but numerically, you can find the solution. What we are interested, before this, you can derive a formulation of second law of thermodynamics and first law of thermodynamics, okay? Believe on me, you can solve everything this, and what you are interested. This, unlike the previous model, this model presents a phase transition. And this is the first point I would like to investigate. The second point I would like to investigate the behavior between power and efficiency. One point I have not discussed you is when you have the maximum efficiency, we have this, the power vanishes. This is the meaning of the Carnot efficiency. Carnot efficiency is the maximum efficiency, but is not useful in the practice because the power is zero. What means we have affinity work, but we need to expect an infinitely long time to derive the infinite many quasi-static process. So this is one reason that the ideal efficiency is not useful in the practice, because in the practice the system operates at finite power, okay? Keep this information, okay? So we are interested in the performance, power and efficiency, and the phase transition properties. Okay. Forget, for instance, the black and the red curves, okay? Pay attention in the blue curves. The blue curves shows a phase transition. Here is the magnetization, the order parameter. This is a typical ferromagnetic transition. We have two ferromagnetic phases dominated by up and down spins. You heat up your system. Here the temperatures are fixed, but you are decreasing the temperature is similar, okay? And you have here the phase transition. The phase transition is continuous, and you have this critical exponent. This beta 1/2 is the typical mean field critical exponent for the Ising model, okay? Now, take in account the blue, the red and the black curves. When this non-conservative force is finite is taken into account, we favor some transitions when are placed in contact with the cold bath, and the other way around when placed in contact with the hot bath. What we have? The phase transitions are split in two different phase transitions. It does not coincide anymore. This is the first main point. So we have a splitting of a phase transition. It's strange, because here we have two phase transition. It's two ferromagnetic phases, coexistence, and you have the spontaneous breaking symmetry here. Now, the spontaneous breaking symmetry is broken, and both phase transition occurs in different points. More than this, while phase transitions dominated by down spins are second order, phase transitions dominated by up spins are first order. This is the second remarkable change. The third remarkable change, the critical behavior here is different from here. Here is the typical ferromagnetic, if you study the phase transition in the Ising model by means of a Landau approach, by the solution of magnetization, you will obtain this critical exponent, because you have only even powers of your magnetization, only odd powers of them. Here, in this case, this is broken, and it gives rise to a different critical exponent
So
in
the
the
case-
mean field level.
In the case f equal to 0, effectively correspond to the system being isolated because the buff do nothing. So you recover.
No, no. If F is equal to 0, but the temperatures are different, the system is out of equilibrium.
Okay, but still you recover
The
standard
phase transition
of the
is
Ising.
qualitatively the same.
I see.
But, good question, when the temperatures are different and the driving are different too, you have this splitting. But good question, important question. If this splitting of a phase transition only occurs when both are different. Temperatures are different and non-conservative drivings are different. Okay, this is what we have in this paper, okay? In this draft, it has not been published yet. Okay, now these mechanisms are robust. If you consider here delta is different from 0, we have the same splitting, but both phase transition becomes first order, and this is also verified in square lattice topologies. Okay, I don't know if I have more time. 2 minutes, may you give me 2 minutes, okay? This is interesting because here, this is the question about the model dynamics, okay? When you have collective system, the interplay between different temperatures and driving, a non-conservative driving, first in the dynamics, you affect the phase transition. But in the thermodynamics, we have these phases, both order phases, phases dominated by down spins can operate as a heat engine, but not the phase dominated by up spins. This phase dominated by up spins is less dissipative and present less lower fluctuations for the range of system, okay? Okay, this is a second important point. And the next conclusion, this setup, if you change the temperature, if you consider a competition between interaction energy, individual energy, it's also possible to project the system to operate in a region close to the maximum power and close to the maximum efficiency. Of course, the second law of thermodynamics forbids this, as I told you previously. If the system operates at ideal efficiency, it has to operate at 0 power. This is not a violation, because this happens here. But there is a region in which a very small range of parameters that the system nearly operate at both conditions. Okay? Of course, when you have the very small temperature, you both coincide. But it's an advantage of this system is that you can project your parameters in such a way there is a small or a finite region in which your system can project approximately at maximum efficiency and approximately at maximum power. And this is what the dreaming of this subject in stochastic thermodynamics. It's improved both as much as possible, okay? Now, I don't have time. I consider the role of collective systems, but the role of the topology, in some cases, the topology can be important. Here, a minimal heat engine, it can be important. And to conclude, in a similar, in the line what I have just told you, we typically desire to optimize both power and efficiency. Typically, if you optimize the power, you decrease the efficiency and vice versa. For this reason, different papers have considered what we know reward function. You consider via Pareto fronts. You calculate, you try to optimize both without sacrificing a quantity, okay? In this study, I consider this for that minimum system, two-state system, and for our collective system, I am going to show only for the two-state system, and what we show. When you include a non-conservative drive in the dynamics, Pareto fronts, here is the line of maximum power and maximum efficiency, okay? And they are convex. And when you include the non-conservative driving, in this case, it becomes concave. Okay, what you can interpret this here, something like that, a smooth phase transition, and here a discontinuous phase transition. Physically, it means, in this case, the maximum power, the maximum Pareto front can be reached via intermediate powers. And in the concave case, you only can consider via the maximum power. Okay, this shares some similarities with phase transition. Okay, to conclude, we have a collective system, can be promising tools for non-equilibrium machines. We have different changes, remarkable features when compared with the equilibrium case and individual energy. In particular, phase transition without equilibrium and non-equilibrium analogs. The role of topology and the time spent can be important. Sorry, I didn't have time to show this. And I have considered different optimization rather than individual optimization of power or individual optimization of efficiency can be interesting and can lead to some changes. Okay, thank you again. Thank you for the audience.
Thank you. Time for questions.
Okay, just wear my glass.
Low dimensions, mean field will not be so good, at least in the equilibrium. Is this the same situation here?
A low dimension system?
Yeah, say 2 dimensions instead of, because you use mean field approximation.
Okay. Okay,
model.
no, just let me see. Of course, quantitatively not, but qualitatively yes. For example, these stars X are results for the square lattice topologies, okay? Here, the system is fully constrained in the order phase, so the topology are not important. But here, in this case, the phase transition properties are different. Here is the mean field. This is not mean field. This is a square lattice. The results are qualitatively similar, but quantitatively different. This case, which is for 0 individual field, it should be investigated. I have not investigated. I'd say I'm not sure.
So I have a simple question. Can you realize these theoretical models in actual physical systems, compare simulations with data?
Good question. I mean, I don't know. I mean, this simple two-state system can be realized experimentally. Okay, I don't know more details, but it has been realized experimentally by via this quantum dot experimentally have been reproduced. The collective system, I don't know.
We have many questions.
Back when you show the derivation of the second law of thermodynamics, you use the channel entropy, right?
Yes.
Would be different? Is it obvious? And it works if you use another entropies like Boltzmann? Because for me it seems very
In the equilibrium case, assim, in the classical case, in the classical thermodynamics, I have not seen many papers. This has been more considered in the quantum case, in the quantum thermodynamics. I'd say, I mean, I'm not sure, but I'd say that would be possible to find a formulation of first law, a formulation of entropy production, which is always positive or non-negative. The definitions might be different, of course, but it will be possible to find some similar. But it's important. It's an important point you mentioned. It's an ansatz. We define the channel entropy. Another entropy definition would lead to a different formulation. It's reasonable to expect to obtain a not equal but a similar entropy production definition.
So, thanks for the talk. It was very clear and very good. So my question is, you define the process through a master equation that deals with classical probabilities. But you said that this work can be applied to nanoscale systems. So how could you deal with quantum correlations? And,
no, in this quantum, I'm not an expert in this quantum case. I would like to be, because it's very interesting. Probably Dario has more knowledge to say. In this quantum case, I also required a formulation like the master equation. Typically, it's the Lindblad approach. I'd say that it's possible to derive. We also have a definition of first law. We also have a definition of second law, but the framework is different. Typically, one departs from the Lindblad equation. Am I correct?
I mean, that was actually something that I wanted to ask. I mean, to me, superficially looked that this framework is a little bit like taking a density matrix, put all the coherences equal to 0, and you work only with the diagonal part of the density matrix. And these are the populations that you are talking about. So actually, I was also curious to see, okay, let's put the question differently. You said that there is an experimental implementation of the two-level systems, right?
Yes, I just the
not by you, but,
the experimental verification has been, most of cases are typically optical tweezers to Brownian systems. Please do not ask me, because I don't have more detail. I don't know more details, but we have several experiments with optical tweezers. Okay, in the case of Brownian Nonequilibrium system. In the case of master equation systems, these experimental situations with quantum dots have been reproduced.
And in that case, the quantum effects are negligible, so you can treat everything with just, let's say, the populations.
Yes.
I see. So you work in a diagonal ensemble.
Yeah, I'd say yes. I'd say yes.
Okay. More questions? You want? Yeah, please.
One point. It has been some works that reproduced these trademarks of thermodynamics in electronic circuits. It has been some works. Okay.
Please. So, is there a way to work with non-Markovian systems, like systems with long-time
good question.
correlations?
There are some papers, there are some works that have worked with non-Markovian systems. I don't know the details, but in principle, yes, I'd say yes.
You still can obtain like first and second laws for them?
Good question, I don't know. I'd say it might be possible, but I would expect it might be possible, but I don't know. I have not studied this.
Okay, thanks.
I wanted to talk about that definition of temperature, because it seems a little strange to me that it depends on both, because the entropy depends on both the system you're interested in and the bath.
Yes.
So if like you had an equilibrium situation, there would be no entropy. So that temperature would necessarily go to infinite. So, but
No. This is the inverse of temperature here. Here is this over. Is this? This is a definition of temperature. This is when you study the stochastic process, you study this side. Okay, you have this: the transition rates and the probability distribution. This is one part. If you want to relate with macroscopic quantities, you should have a way to introduce the temperature there. The commonest approach is this. We define the ratio of this. Okay. No. Okay. This is the detailed balance, okay? Now, typically, what we consider is this. If you take in account this NM is the inverse of this, because the energy difference is an odd function. This is an odd function. So this rate is the inverse of this, because it's this M. Okay? For this transition rate, we will have this. For this rate, we have this transition. If you calculate the ratio, this is minus this, so you re-obtain my previous slide. Now, the transition rate is associated with this quantity. This quantity is the microscopic heat, the heat exchanged in this transition, and this is the associated temperature. This is the typical approach, the commonest approach to to make the connection with the thermodynamics.
okay, thanks.
More? Okay, if not, we can thank Carlos again.
Olha, tudo bom? E aí, e o pós-doc aí? Só em julho? Thank you for the invitation.